All right. Uh, well, so hello, I guess. Good afternoon, good evening, good morning, depending where you are. Uh, I'm Leon Balents. It's a pleasure to be here for this virtual Les Houches meeting. I had been hoping to enjoy the uh, fresh mountain air of the French Alps, but we'll just have to enjoy only the physics. So this is the first of two lectures. I planned this one as kind of an introductory lecture on background material, really, that I hope will be useful for, in particular, for understanding Alan McDonald's lectures in the coming couple of days. So I'd like to talk a bit about 2D materials, which have really exploded in the context of moire patterns in the past 2 years, and review some of the useful concepts and aspects of topology at a very minimal level that might be useful, especially in Alan's second lecture when he talks about twisted bilayer graphene. In my second lecture, at the end of the week, I'll cover some very different subject. Okay, so this is the first lecture. As I said, it's going to be kind of a primer on 2D materials and topology. So since 2018, really since the American Physical Society meeting in March of 2018, the whole condensed matter community has been really overwhelmed by the excitement in the discovery of strong correlation phenomena in twisted bilayer graphene, which has since expanded to a variety of other two-dimensional van der Waals materials. In particular, at that point, Pablo Herrero announced their work discovering correlated insulators, superconductivity in twisted bilayer graphene. Since then, there's also been very interesting reports of strongly correlated metallic behavior, what is typically called strange metal behavior in twisted bilayer graphene. And the list of exciting phenomena continues to grow. I think one of the more interesting things that has been conclusively discovered in twisted bilayer graphene recently is the discovery of a spontaneous quantum anomalous Hall effect, which is a more exotic type of ferromagnetism with a spontaneous zero field quantized Hall conductivity. What's especially remarkable about it in twisted bilayer graphene is this occurs in a system with no intrinsic magnetism at all, no local moments, etc. There have been, as I mentioned, a big growth in other types of moire systems. Just within graphene, there are a variety of other systems. You can now find studies of a bilayer twisted on a bilayer, trilayer moire, monolayer on bilayer, etc. And there's a growing family of heterostructures, moire structures involving not graphene at all, but transition metal dichalcogenides, like, for example, molybdenum diselenide or tungsten disulfide in both hetero and homo bilayers, which I guess Alan will talk about in his first lecture. So what's really interesting about these systems, and what's really kind of remarkable is they take a material like graphene, or in these TMDs, which are just semiconductors, which are, in many ways textbook two-dimensional electron gas systems. Indeed, many of us, when we teach a condensed matter physics course, solid-state physics course, will use graphene as an example to illustrate examples of two-dimensional electron gas physics, and then make them behave like like strongly correlated transition metal oxides, which of course you've heard a lot about in this school. This is kind of a remarkable feat. I want to comment though on exactly what aspect of it is really new. And one should not forget, and it's actually important for the understanding of these systems, that semiconductors and graphene are systems where the study of correlations is not new. In fact, there are many old examples of strong correlation effects in two-dimensional electron gases, the classic one being the 2D electron gas formed at an interface between gallium arsenide and aluminum gallium arsenide. Most obviously, the fractional quantum Hall effect was observed in 2D electron gases. It's certainly due to strong correlations. There are many other phenomena of correlations that are observed in 2D electron gases, for decades. Coulomb drag between two nearby 2D electron gases. In higher Landau levels, there's been a very exciting period of study of emergence of different types of spatial structures like bubble phases, stripes, nematic phases in higher Landau levels. 2D electron gases, when you pattern them into other structures, have also been made very often into systems that show other types of correlation phenomena, like, for example, the Coulomb blockade in quantum dots that are made from 2D electron gases. There's a famous 0.7 anomaly that was studied in quantum point contacts, which are constrictions of 2D electron gases. And for example, the metal insulator transition in MOSFETs is another example. So these are all strong correlation phenomena that really are very beautiful and were investigated heavily in systems like semiconductor 2D electron gases and many of them in graphene as well. So what's really new? What's really new in these Moiré systems is that, or what's, maybe I should say instead, what is really different in these earlier examples from the strong correlation physics that are studied in, for example, transition metal oxide, is that even though they're strongly correlated, these 2D electron gas examples have completely forgotten the atoms, the atomic lattice. That is to say that electron gas in a semiconductor is widely regarded as the classic example of a realization of what's sometimes called jellium, which are just a continuous electron gas with quadratic dispersion, for example, in a semiconductor like gallium arsenide. There are correlations; they experience Coulomb interactions, but for all practical purposes, it's as though those electrons do not experience any periodic potential anymore. That still, as I've said, results in a lot of correlation physics that can be studied, but it's missing some aspects of those phenomena that are central in the study of correlated quantum materials like transition metal oxides, in particular, for example, the Mott transition, where electrons, due to correlations, will enter a state where their wave functions are localized and commensurate with the lattice, the underlying crystal lattice. So what's really new in the Moiré physics is that the Murray physics brings back the lattice. Mark, I think that's basically where I got to. So I think we could cut it